Hello. Today's video will be on interference, a topic from waves. So let's get started. But before interference, I want to talk about superposition of waves. Superposition, if I want to just describe in one word what is superposition, so it is nothing but overlapping of waves. So if you have two or more disturbances, remember wave is nothing but a continuous disturbance being produced. So it's just overlapping of waves. But it is so different from when two or more particles meet each other. Let's just see what I'm trying to say here. Suppose if there's a string from one end, one of the friend produces a pulse and the other end, another friend is producing a pulse. This one is giving, let's say, 2 centimeter amplitude, and this one is giving 1 centimeter amplitude. Now they travel towards each other, and when they meet, the total displacement of the pulse would be 3 centimeters. So this is where superposition is happening, overlap is happening. Now the interesting thing happens. So when they overlap, the resultant amplitude or displacement is the sum of the two. The minute this overlapping is done, the two behave as if nothing ever happened. This one kept moving, so the 1 centimeter one kept moving in this direction, and the 2 centimeter one kept moving in this direction. So their individual properties are not affected because of this superposition happening here. So now we are focused on this area. When they overlap, what happens? What are the different effects of this overlapping? Before that, let's just write or understand the definition of superposition. So superposition is overlapping of waves producing a resultant displacement. I'm using Y for displacement. Resultant displacement at the time of overlap as a sum of individual displacements produced by the waves. Okay, so that's superposition. Now superposition of the waves can produce different phenomena. I'm going to write. So the umbrella is of superposition of waves. This could produce 4 kinds of phenomena, broadly speaking. One is interference, the one we're doing today. Second is stationary waves, next video. Third is beats, not required for A levels. And the fourth is complex waves, kind of noise, but not required again. So we just need these 2. So today we're starting an interference. So what is interference? It's a type of superposition. Now, what is the condition when the superposition of 2 waves is known as interference? What condition? When is the superposition results into interference? So first that, okay? So first, okay, let's just do this question first. I kept this question on the superposition part. So go ahead and solve this. Ignore this dot. This dot has no significance here. Yes, you're right. The answer is B. Now, for interference to happen, we need to first understand what's the meaning of coherence. So coherence means 2 waves should have same frequency. So if I say 2 waves are coherent, what does that mean? It means that they should have same frequency and a constant phase difference. So I'm just going to write constant phase difference. Okay, so these are the 2 conditions for the waves to be coherent. If the waves are not coherent, you cannot get interference. You can get superposition, but that would not fall under the category of interference. For interference to happen, the 2 waves should be coherent. Now you understand what is frequency. For phase difference is, to understand phase difference, first let's understand a wave. So let's say, I'm just going to try and make a wave here. Okay, so a wave which has, oh, that's a nice one. Okay, for once my handwriting did not deceive me. So A and B. Okay, two particles on a wave which have same position and same velocity. They are both at the maximum height and the velocity at that point is 0. So A and B are said to be in same phase. A and B are in same phase, or phase difference of 2 pi. Now, why same phase and 2 pi are same? See, consider this. If, let's say, if a point A and a point B. Point A was already there. Point B moved the whole circle and came to point B. Point A. So now A and B are at the same position on a circle. So their phase difference is either 0 or it is 2 pi. Or if it would have moved 2 circles, it would have 4 pi. If it would have moved 3 circles, it would have been 6 pi. So pi, 2 pi means 360 degrees. It's just radians. Pi is in radians. Now, path difference is the distance between the 2 points. So path difference between A and B is lambda. Next is time difference. Time difference between A and B is time period of the wave. A wave would take time t to move from A to point B. Okay, let's understand it in more detail. Okay, let's just make this diagram again. So I have a wave. Okay, now consider this, a point A and a point B. Now A and B are at the same position. They are both at the starting position, but then A is about to go up and B is about to go down. So A and B have a distance of half a wavelength and a phase difference of pi. Okay, let's see another particle. What about A and C? A and C has a path difference of wavelength and a phase difference of 2 pi. Let's try another particle. Let's say a particle at P and a particle at Q. Now you try. What's the path difference? The path difference is lambda over 2 and a phase difference of pi. So remember this. A phase difference of 2 pi means a path difference of lambda. Now, let's say a wave is moving, a wave A, and another wave which is coming from behind. This distance is now, let's say, lambda. So what's the path difference between them? Is lambda. If it is coming from further behind, let's say wave C, and the distance between A and C is, let's say, 1.5 lambda, then what's the path difference? Delta x is for path difference, 1.5 lambda. Okay, let's do one question. Two waves arrive at a point when path lengths are 5 meters and 5.6. So what it means is that there's one wave which has traveled 5 meters and has reached here. Another wave has traveled a little extra distance, 5.6 meters. So what's the path difference? Their path differences, because this path difference would then help me decide what it would look like on my interference pattern. That's why we need to know this. So now my path difference is 0.6 meters. Now we need to convert this in terms of the wavelength. Wavelength is 0.2. Both of them have same wavelength. So my path difference is 3 times the wavelength. So that's my path difference. Okay. What is the phase difference? Same question. So if my path difference is 3 lambda and 1 lambda has a path phase difference of 2 pi, so my path difference would become then, my phase difference is then 6 pi. That's it. Okay, another one. If a path difference is lambda over 3, go ahead, pause it and do it yourself. So if path difference is lambda over 3, my phase difference in that case would become, so change of phase, okay, let's just write phase difference is 1 lambda is 2 pi, so it'll be 2 pi over 3. That's it. Okay. Now interference. Now what kind of superposition of what kind of waves would produce interference? First that. So first condition is the waves should travel in same direction. Okay, if they are both moving towards left, they should both move towards left. If one is moving towards right, the other should also move towards right. Travel in same direction. Second, the waves should be coherent. If the waves are not coherent, we cannot observe interference. And it is very difficult to observe to get, should be coherent. It is very difficult to get coherent sources, especially for light waves. That is why it is very difficult to observe interference. Now, how do we, what is interference? This is a condition. What is interference then? The interference is, so if you have 2 waves, okay, one slightly starting from behind, so that there is some path difference, or there is some time difference. One starts at t equals to, let's say, 12 o'clock, and this one starts at 12:10, or there's some time difference. So because there's a time difference, there will be some path difference. Say, let's say one wave starts from behind and there's a path difference. These 2 waves reach a screen. Depending on how much distance have they traveled to reach the screen, because if they reach exactly this position, the distance traveled would be different. If they reach this position, distance traveled would be different. So depending on the position on the screen, a pattern is observed. So you will have an alternate positions of maximum and minimum intensities. So this is your interference. So what happens in interference is, whenever 2 waves interfere, you have alternate positions of maximum and minimum intensity. So that's your interference. So if it is maximum intensity, it is called constructive interference. So this one is maximum intensity. And if it is minimum intensity, this is destructive interference. Now what happens is, let me just try and draw a diagram to explain that. Let's say, for example, this is one wave reaching at a point. and the other way, the one reaches exactly like this. So the path difference is here. They are both at their maximum. They're at their maximum amplitude. So the resultant wave would be this. So the amplitude A has become now 2A. Whereas if it is destructive interference happening, then if this was one wave, another would be like this. So this is A, and then resultant is 0. So resultant amplitude would be then 0. So this is destructive. So when you have maximum amplitude, you would have maximum intensity. Minimum amplitude, minimum intensity. Okay, let's try and show you one. So if this is my wave, okay, and another wave comes like this. So see, maximum. So what is this one? Is one wavelength ahead. So if it is one wavelength ahead, or two wavelengths ahead, or three wavelengths ahead, what kind of interference is happening? Constructive. So for constructive interference, path difference is n lambda. So either one wavelength ahead or two wavelengths ahead. If it is destructive, let's try and draw a diagram here. So if you want a destructive, so you want a peak to coincide with a trough. So what's the minimum you want? So when you have as a trough, what you want here is a peak, a trough, a peak, a trough, and so on. So see what's a minimum path difference here? Lambda over 2. So if the path difference is lambda over 2 or 2 lambda over 2, no, 2 lambda over 2 would become constructive. So 3 lambda over 2, 5 lambda over 2, and so on. So now the path difference is an odd multiple of lambda over 2. All right, so if it is an odd multiple of lambda over 2, so in that case, you will have what kind of interference? Destructive. Otherwise, it will be constructive interference. For constructive, it should be an integral multiple of lambda. Okay, now what is the relationship between the intensity and the amplitude? You just need to know this, that intensity is proportional to amplitude squared. So at constructive interference, so whenever it is constructive, what is happening? Amplitude doubles, and because intensity is proportional to amplitude squared, intensity becomes 4 times. And at destructive, because amplitude has become 0, look at this, destructive, resultant amplitude has become 0, so intensity also becomes 0. So whatever was the intensity supposed to be at destructive interference, it goes to constructive. So that's why it's just a redistribution of energy. Interference is nothing but the redistribution of energy. The energy which was supposed to be at the destructive part of the interference, it goes to the constructive. Okay, go ahead, pause and do the question. The answer is this. Okay, wavelength is 0.4, path difference is 1 meter, so this is 1, lambda is 0.4. Let's see what multiple it is coming. So my 1 divided by 0.4, this is giving me 2.5, which I can write as 5 times 5 over 2. So it's 5th multiple of lambda by 2. So the interference is destructive. If it is not integer, it is destructive. two waves have a phase difference of 3 pi by 2. So if the phase difference is 3 pi by 2, now we know 2 pi is lambda, pi is lambda over 2. So what is the path difference then? So path difference, I'm just writing, instead of pi, I'm writing lambda over 2. So this is 3 lambda over 4. That's my path difference. Okay, every pi, just to show the diagram here, say if it is, okay, that's horrible drawing. Let's just get the eraser. So if there is a wave and the path difference between any 2 points is a wavelength, the phase difference between those 2 points is 2 pi. So pi will be lambda over 2, and that's why this. Two waves interfere with path difference lambda over 2. So path difference is lambda over 2. So that means it is destructive. And that's why the resultant intensity is 0. Individual intensities are not 0 as a resultant. Okay. Light from two coherent sources. What is coherent sources? Same frequency, constant phase difference. So 2 meters. Another is 2.75 meters. So what's the path difference? 0.75. 3 times the wavelength. So dark. The point is dark. Now, this is the experiment that proved that light has wave nature. Before this experiment, it was assumed and considered, even by Newton, he gave his famous corpuscular theory that assumed that light has particle nature. Young's double-slit experiment done by Thomas Young in, I think, 1905 to prove that the interference which is done by sound waves, which is done by water waves, is also done by electromagnetic waves, and hence the electromagnetic waves should be wave nature. So after this experiment, it was accepted all over that yes, electromagnetic wave or light has wave nature. Now, what was this experiment about? Now, you know why before this experiment no one could ever prove that light has wave nature? Why light did not show the interference pattern is because of the coherence. We could not get a source of light, two sources of light which can give light with the same frequency or constant phase difference. Now what this gentleman did, very smart, he used one source of light, and using that source he then used 2 slits. Light from this source came and the light from this source came on this slit, and now what do we have here? We have 2 sources. Isn't it wonderful? But when he did this experiment with light, normal light, which has many colors, again the pattern could not be observed. I don't know if some of you have ever saw some oil spilled on the road, and if you see that oil from different angle, you see different colors. So that is interference of light happening. So whatever angle you see a color, let's say at one angle you see blue color, so that is a constructive interference of blue color happening at that angle. Rest all the other colors are doing destructive. If you bend your head again and see a red color, then what's happening is all the other colors have become destructive, only the red color is constructive. Now if this experiment is done with a white light, what would happen is you will never get a destructive interference. You will never see a complete dark pattern, because at destructive interference, one or the other color would have constructive. So the important requirement here is that you should have a single color source. A single color source is known as monochromatic. Chromatic comes from color. So obviously, who's responsible for color in light? Frequency. So it's a single frequency or a single wavelength source. So now both the lights are either yellow or either blue or green or red or some invisible color. So lasers could be a better option. So now the two lights coming from here are then received on the screen. Okay, so I have a screen here. Now, these two light waves, when they reach here, they have both traveled the same distance and they are both produced at the same time. So what's the path difference? 0. So what kind of interference is obtained here? So if the path difference is 0, what you have is a constructive interference. So I'm going to use a blue color for constructive interference. So I have here a blue color. So that means a constructive interference is happening. So you'll have an alternate dark and bright fringes will be obtained. And let's say I'm going to make this on the screen. So everywhere you have a bright fringe, this blue one, it would be, the path difference would be an integral multiple of lambda. Okay, so this is happening here. So that's it. Okay, here you go. So that's your alternate. So imagine a light is coming from this source and reaching here, and is also coming from this source and reaching at this point. Now what's happening? So because of this, they will have a path difference now, but then path difference has to still satisfy this condition, and lambda, n should be 0, 1, 2, 3, 4. If it is not satisfying, it would not have been a bright fringe here. And all the places that you see white, the path difference should be odd multiple of lambda over 2. So that's the path difference. Now, this width of this blue thing is called as fringe. And this width here is then known as fringe width. I'm just going to erase this part and write. So fringe width is, so this is the fringe width. So in ideal scenarios, okay, in this experimental setup, the fringe widths are of same size. Now we need to know some derivations here. I'm going to just do that on the next page. Okay. Okay, I'm just going to make the diagram here. So this is my source and this is the slits. So it is important that the source should be exactly at the center, so there's no path difference being produced here. And then this is the screen. So one source of light is here, and then another source of light is here. Okay, so this is one, if you're assuming exactly at the center S, which is producing S1 and S2. So there's no path difference here and here. So here the path difference is 0. They have both traveled the same path. Now here, I'm just going to draw a perpendicular P. Say now my path difference is nothing but S2Q minus S1Q, and which is nearly equal to S2P. So my path difference is this between the two waves. Now if the distance between the two slits is small d, and I'm assuming this angle to be theta, so we'll just show that on the diagram here. So if I take this angle as theta, let me just use this and see here. So these are my slits, assumptions. So this is my slit 1, slit 2. So this is my path difference. So this path difference delta x is small d sine theta. This is your theta. This is also theta. This is d, and then this will be d sine theta. Okay, so now this d sine theta, if this is equals to n lambda, you have constructive interference at y. And also, if you see from this triangle here, this triangle, which goes all the way to P, what will be tan theta from that triangle? So my tan theta, using my Sukatua, tan theta is y over d. And because angles are very small, okay, so this is assumptions. Your capital D has to be much larger than small d. So then your sine theta will be nearly equal to tan theta. Okay, so what will be my sine theta from here? So I'm going to write this as sine theta is equals to y over d, and then I'm plugging here d sine theta is n lambda, dy over capital D is n lambda. So my y is n lambda capital D over small d. So that is my position of bright fringe. So y is the position of bright fringe. So if I have, let's say the first bright fringe will be lambda d over d, and then second bright fringe will be 2 lambda d over d. So if I subtract them, I'll get the fringe width. So let's write that. So my fringe width is just the difference of the two. So that will be, see, I'm going to write here my second bright fringe would be at 2 lambda d over d. Okay, using this equation, remember n is just an integer. It tells you the position of your fringe, say 2 lambda d over d, and then y1 is 1 lambda d over d. So if you subtract them, so what you get is the fringe width. So if I'm going to do that, so this is the fringe width. So I can make my fringes wider if I take the screen away. So if I increase this d, my fringes would become, say, if I want to make my fringes a little bit wider, I need to increase this distance d, or I need to decrease this distance small d. Or if I, instead of using blue color, if I increase my wavelength, it depends on the wavelength too. So if I use blue color or red color light, which one do you think would give me wider fringes, because it's giving fringe width? So red color would give me wider fringe because red color has higher wavelength. D, capital D and small d is a setup of that experiment, and then depending on the color of the light you use, you get broader or thinner fringes. Okay, let's do one question then. Monochromatic single wavelength from a laser passes through 2 narrow slits separated by 0.25 mm. So my small d is 0.25. Don't forget to convert mm to meters. An interference pattern is observed on a screen placed 1.8 meters from the slit. So this is my capital D. The distance between 8 consecutive bright fringes. So they have given you the distance between 8 consecutive bright fringes. So what is fringe width? dividing 21.6 by 8 will give you the fringe spacing or the fringe width. So 21.6 mm divided by 8. So using my calculator, 2.7 mm. Okay, so this is done. Use your calculator, work with me. Do not just see the video, just do the questions. It'll make your mind remember more. Calculate the wavelength of the light. So now I know the fringe width, so I'm going to use fringe width, convert into meters first, equals lambda, we don't know, capital D 1.8, small d 0.25 times 10 to the power minus 3. Use your calculator and the answer will be, rearranging, you can rearrange it. So 3.75 10 to the power minus 7. Okay, I'll just rearrange here for you. So 2.7 times 10 to the power minus 3 times 0.25 10 to the power minus 3 divided by 1.8. So this is giving me answer as 3.75 10 to the power minus 7 meters. The student repeats the experiment using light of shorter wavelength. So if you decrease the wavelength, what would happen? State. So first state and then explain. So state, what is the effect? Effect is the fringes becomes smaller, the fringes become closer together. Why? Because smaller the wavelength. So lambda d over d, as lambda decreases, because lambda is decreasing, explain. What's the effect? The fringe width decreases. Okay, just wanted to show you this animation. Just bear with me, let me just take you to this animation. Alright, let's see. Alright, so this is what I wanted to show you. Okay, let's just choose the lasers. So these are my lasers. I'm using less wavelength. Higher frequency means less wavelength. I need a screen. I need double slits, and let's just put the slits here. Okay, bringing this. I want 2 slits and okay, slit width, little bit, this is my slit width, and I need a screen. Where is the screen? Okay, we're not using the graph so much right now, so let's just use lasers. Oops. Okay, so just moving this closer. 2 slits. Oops, show me 2, and then screen. Okay, and a little bit slit width, we're decreasing. All right, let's start then. So, right, so just waiting to see the interference pattern. So here you go. So can you see the fringe width? Okay, so the fringe width is, now I can now change the fringe width. So if I decrease the frequency, I'm increasing the wavelength. So what do you expect? Pause and say, what are you expecting? So because the wavelength has increased, the fringe width has decreased, and you can see less fringes. Can you see how wide they are? With green, you were seeing proper 3. Okay, let's just try and make it purple. So the fringes would decrease now, fringe width would decrease, and you'll see more fringes on the same screen. If I'm not changing anything, I'm not changing capital D, which is the distance to the screen. I am not changing the distance between the slits. So can you see proper 3 fringes you can see now? Okay, so that's your interference pattern happening. Okay, let me just explain you through this. So what happens in the interference pattern is, you have 2 light sources, condition is coherent, they're both moving in the same direction, and you observe a pattern of dark, black, bright, purple. The pattern is interference pattern, constructive and destructive. That's it. So that is your interference happening here. All right. Okay. So let's just do this question. If the fringe spacing is 2.5 mm, so the fringe spacing is 2.5 mm. Find distance of the fifth bright fringe from the center. So now you want y, the fifth bright fringe from the center. So just using, so 5 times, I think we have to go back to the previous question. And, oh no, we don't need it. So what is this now? This lambda d over d is the fringe width, and you just times it by 2.5. So that is 12.5 mm. That's it. Okay, so now just try and go through the interference thing once again. It is quite a lot to take. When you redo the video, take a book and a pencil, do the question with me, try to understand the concept, try to guess what's coming next, and I'll see you again. Thank you so much for learning. Keep learning. Bye bye.